Today we're assembling what we're calling the Time Traveler's Toolkit. Our mission here is to equip you with the essential theoretical framework, concepts you need to understand, model, and maybe even forecast data that's collected over time. A time series is, at its heart, quite simple. Just observations recorded one after another. Think stock prices, temperature readings, website visits. But unlike data where order doesn't matter, here, sequence is, well, everything.
It really is. The sources define a time series formally as a realization of a stochastic process. Now, that sounds a bit heavy, but it just means a sequence driven by chance, unfolding over time. Like those stock prices you mentioned, or maybe hourly rainfall. Probability governs it, time indexes it. And the key thing, the past often gives clues about the future. Our job is to figure out how, mathematically.
Right. So regardless of the field of economics, climate science, whatever the fundamental goal seems to be consistent. You want to understand the series, identify any predictable patterns, maybe strip them away, and then use what's left, the sort of core randomness, to understand the process and maybe predict what comes next. To do that effectively, we need to cover, I think, three main theoretical pillars today: decomposition, stationarity, and the tools used to measure dependency. Okay, so let's start with decomposition. When you first plot time series data, it can look pretty chaotic. But the idea here is that this complexity isn't just random noise, right? It can often be, well, broken down.
Exactly. That's the essence of decomposition. We try to express the observed series, let's call it Y sub t, as a combination of distinct components. Usually it's thought of as either adding these pieces together or multiplying them.
And what are these pieces? What's the first one we typically look for?
The first is often the trend. Think of it as the underlying long-term direction or movement in the data. It represents the slow change in the average level of the series over a long period. It could be a steady increase, a gradual decrease, maybe even something curved like a quadratic. But it's the main trajectory.
Okay, the overall slope, more or less. Then, layered on top of that, we often see regular ups and downs.
Precisely, that's seasonality. This captures the predictable, periodic fluctuations. The absolutely crucial part here is regularity. Seasonality means patterns that repeat over a fixed time period. Think monthly data with a yearly pattern, that period is 12, or daily data with a weekly pattern, period 7. It's clockwork.
That makes sense. Predictable cycles. But the sources also mention irregular cycles. How is that different? If it's a cycle, isn't it seasonal?
Good question. Irregular cycles are also wave-like movements, but their duration isn't fixed or predictable like seasonality. The classic example is the business cycle in economics. You have booms and busts, but they don't happen every, say, 48 months exactly. Because they're harder to pin down, in many introductory analyses, these irregular cycles often get lumped in with the final component.
Which is?
The residual, or the error term, often written as epsilon sub t. This is what's left over after you've accounted for the trend, the seasonality, and maybe any obvious long cycles. It's the unexplained random variation. Ideally, we want this residual part to be as simple and unstructured as possible, like pure noise.
Okay, that idea of getting down to simple, unstructured noise seems like a perfect lead into our next big concept: stationarity. Why is this so fundamental? Why do analysts put so much effort into sometimes forcing their data to look stationary?
It really boils down to reliability and predictability. Think about it. How can you build a reliable model if the underlying rules of the system keep changing? Stationarity means the statistical properties of the process generating the data, its mean, its variance, how it correlates with itself, don't change over time. If a series is stationary, its behavior today is, statistically speaking, similar to its behavior yesterday or last year. That consistency allows us to use the past to infer things about the future.
Okay, consistency is key. What are the sort of main conditions for a series to be considered stationary?
Broadly speaking, there are three main requirements we look for. First, no systematic change in the mean. That means no underlying trend. The average level should be constant. Second, no systematic change in the variance. The fluctuations around the mean should be roughly consistent in magnitude over time. No periods of suddenly high volatility followed by low volatility. And third, no strictly periodic variations. Any strong seasonality should have already been removed.
Now, I've heard about different kinds of stationarity, weak versus strict. Is that distinction important in practice?
It is, conceptually. Strict stationarity is the really strong definition. It requires the entire joint probability distribution of any set of observations to be unchanged if you shift it in time. That considers all statistical moments, and honestly, it's almost impossible to verify with real-world data.
So not very practical then.
Not usually, which is why we rely on weak stationarity. This is the workhorse definition in applied time series analysis. Weak stationarity only focuses on the first two moments. It requires just two things. One, the mean value is constant and finite over time. Two, the autocovariance, how strongly observations are related to each other based on the time lag between them, depends only on that lag, not on the specific point in time you're looking at. So when people just say stationarity, they almost always mean weak stationarity.
Okay, so constant mean, constant variance, and correlation depends only on the lag.
Yeah.
That seems much more manageable. If we manage to transform our data, perhaps by removing trend and seasonality so the residuals meet these conditions, what are the simplest forms this stationary residual might take?
Well, the ideal scenario, the target really, is to get residuals that are white noise. A white noise process is simply a sequence of random variables that are uncorrelated with each other, have a mean of 0, and a constant finite variance. If your residuals look like white noise, it suggests your model has captured all the predictable structure, all the systematic dependence in the data. There's nothing left to explain, essentially.
Is that related to IID noise?
Closely related. ID noise means that the random variables are not just uncorrelated, but also independent and drawn from the identical distribution. White noise only requires uncorrelatedness, which is a weaker condition than full independence. But for many modeling purposes, getting residuals down to white noise is sufficient.
And what about a process that's famously not stationary, like a random walk?
The random walk. It's a fundamental building block, especially in finance. The simplest form is today's value equals yesterday's value plus a white noise term, a random step. The crucial thing about a random walk is that its variance increases over time. It grows linearly with the time horizon. Because the variance isn't constant, it violates that second condition for weak stationarity. This makes it fundamentally non-stationary and much trickier to model directly without transformation.
Okay, so let's assume we've done the hard work, we've maybe differenced our data or removed a trend, and now we have a stationary series, probably our residuals. Now we need to understand its internal structure, its memory, how much does the value today depend on values from yesterday, the day before, and so on. We need tools for that.
Exactly. And this is where the correlation functions come in. The foundation is the autocovariance function, or ACVF. For a stationary series, the ACVF measures the covariance between an observation at time t and an observation at time t plus h, where h is the time lag. Because of stationarity, this covariance depends only on the lag h, not on the actual time t.
Covariance can be hard to interpret directly because of units, right? So we normally standardize it.
Precisely. We normalize the ACVF by dividing by the variance of the series, which is the ACVF at lag 0. This gives us the autocorrelation function, the ACF. This is just the correlation coefficient between observations separated by lag h. It measures the total linear association between y sub t and y sub th. Values range from -1 to 1, just like regular correlation, and the ACF at lag 0 is always 1, correlation with itself.
Okay, ACF measures total correlation. So
Yeah.
if yesterday's value influences today's and the day before yesterday influences yesterday, the ACF at lag 2 will pick up that indirect effect through lag 1.
Exactly right. It captures both direct correlation at lag h and any indirect correlation that's transmitted through the intermediate lags. This is why we need another tool. But first, how do we know if an observed ACF value is actually meaningful?
Right. Is it just random noise or real dependence?
For large samples from a white noise process, the sample ACF values are approximately normally distributed around 0. We can construct confidence bands, usually around ±2 over the square root of the sample size. If a sample ACF value falls outside these bands, we typically consider it statistically significant. There are also formal tests, like the Jungbox test, which check if a whole set of ACF values, say from lag 1 up to lag h, are collectively different from 0. It tests the overall hypothesis of independence up to that lag.
Okay, but back to the indirect effects issue. If ACF captures everything, how do we isolate just the direct link between y sub t and y sub th, stripping out the influence of the intermediate values?
That is precisely the job of the partial autocorrelation function, or PACF. The PACF at lag h measures the correlation between y sub t and y sub th after controlling for or removing the linear effect of all the observations in between. Think of it as the additional correlation explained by lag h beyond what's already explained by the closer lags.
So let's say the PACF at lag 3 is close to 0, even if the ACF at lag 3 is large. What does that tell us?
It suggests that the correlation seen in the ACF at lag 3 is likely just an echo. It's being transmitted through the correlations at lags 1 and 2. There isn't a strong direct connection between observations separated by 3 time steps once you account for the steps in between.
I see. So ACF shows the overall shadow, PACF tries to find the direct source of the shadow at each specific lag.
That's a great analogy, and understanding the patterns in both the ACF and PACF plots together is absolutely key for identifying appropriate time series models, which I think is where we're heading next.
Absolutely. We've decomposed, achieved stationarity, and now we have these diagnostic tools, ACF and PACF, showing the dependent structure. How do we translate that information, those patterns of correlation and partial correlation, into an actual predictive model?
This is where theory meets practice directly. The patterns observed act like a signature, suggesting the type of model structure that might be appropriate. The two main building blocks for univariate models using only the past of the series itself are autoregressive AR models and moving average MA models.
Okay, AR and MA, what's the basic idea behind each?
An AR model, say ARP, models the current value of the series, y sub t, as a linear combination of its own p previous values plus a white noise error term. It's regressing the series on its own past. A moving average model, MAQ, models the current value, y sub t, as a linear combination of the q previous error terms plus the current error term, epsilon sub t, and possibly a constant mean. It's saying today's value depends on past random shocks or surprises.
So AR uses past values, MA uses past errors. How do the ACF and PCF tell us whether to use AR or MA, and what order P or Q to choose?
This is the really neat part. There are theoretical properties for pure AR and MA processes. For a theoretical ARP process, its PACF cuts off sharply after lag P. So the partial autocorrelations are significant up to lag P and then essentially zero afterwards. Its ACF, however, will decay gradually towards zero, possibly oscillating.
Okay, PACF cuts off for AR. What about MA?
For a theoretical MAQ process, it's the reverse signature. The ACF cuts off sharply after lag Q. The correlations are significant up to lag Q and then zero. The PACF for an MAQ process will decay gradually towards zero.
Ah, so you plot the sample ACF and PACF of your stationary data, look for a sharp cutoff in one and decay in the other, and that suggests the model type in order.
That's the core identification strategy, yes. If the ACF cuts off, think MAQ. If the PCF cuts off, think ARP. If both decay, you might need a mixed model, an ARMA model. These ARMA structures form the basis of many forecasting methods.
And this is mostly within the univariate framework, right? Using just the series itself.
Correct. That's usually the starting point. Build a good univariate model as a baseline. Then you might consider multivariate models, which bring in other relevant predictor variables, maybe their lagged values too, to see if they can improve the forecasts beyond what the series' own history tells us.
But the key is always comparing performance.
Absolutely. Always compare models based on their performance on data they haven't seen during fitting, usually a holdout test set that occurs later in time than the training set. That's the true test of a forecasting model.
Well, this has been quite a tour through the foundational theory. We started with just a sequence of data points over time and saw how we can conceptually decompose it into understandable parts. The long-term trend, the regular seasonal rhythms, and that leftover random bit, the residual.
And the absolute cornerstone was achieving stationarity in that residual, making sure its basic statistical properties, mean, variance, autocorrelation structure, are stable over time, because that stability is what allows us to reliably use tools like the ACF and PACF.
Right, those tools that diagnose the memory of the series.
Yeah.
The ACF showing the total correlation, direct and indirect.
And the PACF helping us isolate the direct correlation at each specific lag, stripping away the echoes from closer lags. Understanding those patterns is really the bridge to building effective models like AR and MA.
Okay, so here's a final thought to leave you with, circling back to that simple yet non-stationary process, the random walk. We said it's just yesterday's value plus a random uncorrelated step. Fundamentally unpredictable in the long run because its variance just keeps growing.
That's right. The steps themselves are simple white noise, but accumulating them creates this path-dependent process that can wander anywhere.
So consider this. If something as complex looking and unpredictable as a random walk can be generated simply by adding up lots of small, independent, random shocks, how many complex phenomena out there? Maybe market prices, maybe technological progress, maybe even aspects of our own lives might appear driven by intricate forces, but are actually closer to a random walk. Something to think about as you analyze your own time series data.